chart on the right to let you know that there's a lot of activity and opportunity around augmented reality. While there has been activity germinating for about the last decade, there's been a significant ramp up in the activity in just the last 2 years, specifically with the introduction of ARKit and ARCore this year by Apple and Google, respectively. So why have things taken so long to accelerate? Well, this map of the AR landscape, I think, gives you a really good idea. There are so many different components in creating an AR experience, from authoring tools, image recognition, 3D capture and tracking mechanisms, different devices. None of this easily work together, and certainly not across all sorts of different devices that have been introduced over time. And all that complexity creates barriers. Now, these are the usual barriers that we expect to see as we introduce new technologies. Fragmentation and lack of standards are old friends. We saw cultural barriers as we termed users of Google Glass glassholes. And of course, until we get to scale, the cost of many of the devices that were in the market were thousands of dollars each. So that severely limited the budgets that we could use, and therefore experimentation and deployments into the market. So where are we now? Well, as mentioned earlier, the introduction of ARCore and ARKit changed a lot. It removed a significant amount of complexity for designers and developers to create and deploy AR experiences. Instead of having to stitch together their own composite solutions, they can leverage these new frameworks from Apple and Google. So the bottom line is really that rather than Apple or Google being the winner here, the real winner is the developer in this game. Now, however, I do want to make the comment that although technically there isn't a ton of difference in the solutions from Apple and Google, if I had to advise you on where to invest your resources, I think that it's a no-brainer to focus on the Apple ecosystem. Apple's ARKit can be deployed on any device that runs iOS 11, so literally hundreds of millions of addressable devices today. Now that's orders of magnitude more than the 2 million or so ARCore compliant devices on the market at this time. That will, of course, grow, and there will be a higher addressable market, but if I had to spend your money today, I'd spend it with Apple. So let's talk about AI. There isn't a space that seems more exciting, and if you watch science fiction, inspires more fear than AI. The good news is that we're not really doing AI yet. IBM's Watson is not aware of itself yet, and the Terminator isn't coming for any of us. But part of the problem that I see with AI today is that we use all these different phrases, AI, machine learning, neural networks, deep learning, almost interchangeably, even though they're not exactly the same things. They're all related, but not exactly. And we also ascribe capabilities to AI and machine learning in our minds that just aren't there yet. Today, machine learning and deep learning are much more like supercharged predictive analytics than anything. So it's important that organizationally we understand the differences in these terms and start developing strategies on how we can leverage them in our organizations. I also wanted to quickly share some research that I found from MIT recently on business drivers around AI. Nothing really earth-shattering here. Most organizations across all industries are just scratching the surface with about, say, 10–15% of usage of AI within the organization. And they expect to be much further along in 5 years. They think that AI promises the potential for creating competitive advantage, while many companies also want to embark on AI initiatives as a defensive measure because they worry about competitors gaining that advantage over them, or new entrants coming in and eating their lunch, because they have machine learning and they don't. So, there's a lot of reasons for getting started here, and there's a lot of focus, I think, across all sectors. And while companies have high aspirations around AI, adoption is still fairly nascent. More than half of the companies in the MIT survey haven't even really identified a strategy around AI, let alone deployed anything. And while a fair number are dabbling, only 5% in the survey feel like they've done so in a meaningful and deep way across the organization. So if you haven't gotten started yet, don't worry. You're not really behind. But you better get started. So why is this area of technology so important? Simply, it can help us create better and faster decisions, which in turn will generate more efficient operations and better outcomes. And importantly, these machine learning and deep learning models can adapt as they are fed more and more data, dynamically enhancing their models, refining our responses, and creating deeper insights without the need for manual intervention to improve these models. That's one reason why machine learning and deep learning have taken off in areas like high-frequency trading, where every second and every penny counts. So why have we had this explosion of deep learning in the past few years? Really the convergence of three things: the explosion of data, which we've had for a while, but it continues to advance; more complex algorithms, although algorithms themselves have been around a long time, but really it's the availability of high-powered GPUs, which are just better at parallel processing the type of data in which the CPU was just not well positioned. Further, there are core frameworks like TensorFlow from Google and others from companies like Microsoft, Facebook, Caffe, and Keras, from which to create your own models. And the usual suspects, Amazon, Microsoft, IBM, and Google, have taken it one step further and introduced AI platforms in the cloud for startups and enterprises alike to easily, rapidly, and cost-effectively bring these technologies into their businesses. But you don't have to create it all from scratch. There are some very good on-ramps to using the technology today. There are a lot of good off-the-shelf solutions that you should look to leverage first in the areas of machine vision, natural language, speech, and translation today. Technologies like CoreML from Apple and TensorFlow Lite from Google let you introduce machine learning models directly into mobile applications very easily, letting your mobile developers use the same languages and tools that they're used to using today while getting the full leverage from the preeminent frameworks like TensorFlow, Caffe, or Keras. So get right to work. And then just very briefly, I just want to show this slide just to give you a sense of how pervasive this is across industries, so that hopefully it gives you some more impetus to get going on your own. So the discussion around AI and machine learning leads me to our next topic, the rise of conversational interfaces. These can take the form of chatbots like Google Assistant, or smart speakers like Amazon's Echo, or intelligent assistants like Siri and Cortana. Natural language and speech APIs have improved greatly over the past few years due to deep learning models and provide the capability to unleash chatbots and voice into the enterprise. I wanted to reference this NPD study on the right to point out two things. One is that consumers who don't care how technology works like them, but often find their interactions with them maddening. They don't work like most normal people expect them to act. Sometimes they don't understand us, don't understand what we mean, or they just forget what we're talking about after the first or second follow-on question. I also thought that it was very interesting that voice interaction is used much more frequently on smart speakers than on smartphones or smart watches, even though the same capability is often present there. Just kind of odd. I also think that it's interesting to look at the contrasting interaction strategies between Alexa and Siri. Companies have made thousands of skills available for Alexa, but they each require a specific syntax to invoke the commands, or she has no idea what you're asking her to do. And when you have thousands of different skills to choose from, you have to remember how each of them work, because they don't always follow the same model, and it makes it a little bit more challenging. Siri, on the other hand, can do, doing air quotes, less, but it is way better at divining our intent no matter how we make that request. So for the things that it knows how to do, you could ask the question 5 different ways, or ask them, ask something 5 different ways, and it will know what you meant and be able to take that action regardless of the method that you use. So just think about those 2 different interaction strategies and consider which model that you may want to invoke when designing solutions for your company. Yet lastly, I want to point out that speech recognition is not something that is solved. We have made unbelievable advances in the past few years in the quality of speech recognition using deep learning models. But it's a bit overstated when we say that speech recognition is at human levels. The bar for human level is based on a one-to-one communication between people who speak perfect English and don't interrupt each other. That's just not how the world works. There are still big issues to overcome with regard to accents, background noise, divining intent, and importantly, managing multi-speaker conversations. But I think deep learning will continue to evolve and improve dramatically in those aspects. And the last section I want to talk about is IoT. IoT is, I mean, when you think about from a scale perspective, is going to be absolutely huge. I mean, if you think about, there's 100 to 150 million PCs out there. There's like anywhere from like 3 to 5 smartphones and tablets out there. So you've got orders of magnitude improvement. When you think about IoT, it's even yet another order of magnitude. We're talking about billions, maybe even trillions of devices that are going to be connected in some way, shape, or form over the next decade or more. And you can see here that there's any set of numbers that you want to look at is going to show tremendous, tremendous growth and opportunity. So let's take a quick look at where we are from an adoption perspective. These stats are actually pretty advanced from where one might think it would be. There's almost 40% of enterprises are already actively using IoT, with almost another 30% planning to deploy in the next year. So there's a tremendous amount of activity already, and a lot more to come still. Now, in light of these adoption rates, it's actually kind of interesting when you take a look at some of the statistics around whether or not IT is ready for IoT. And in many cases, they're not really. Number one, like the first one to me is interesting that they don't see the value of monitoring the devices. I think that they need a conversation with the business on that side of things. But the next two reasons why that they're not ready are the reasons why they're not ready for a lot of things. Don't have enough staffing, don't have enough budget. So common problem, and common solution, but that's an issue that needs to be bridged. So I want to talk to you about complexity for a minute. IoT is more about process than technology, but the technology can be a mess. If you thought Android fragmentation was tricky, wait till you get involved with IoT. So a lot of the activity so far in IoT has been around proof of concepts and early pilots. But the real challenge is not in making those work, but in scaling from POCs to production. It's one thing to coordinate the different tools, technologies, and devices for a POC, but when you start rolling out to, say, a dozen different manufacturing sites, that's when the fun starts. Across those sites, you'll have a mix of plants that may be the result of acquisitions, built at different times, and with equipment from different manufacturers, and even use different business processes entirely. Realize that, in the computer-dominated world of IT, the concept of legacy is like 5 years old. In the world of manufacturing and operations, it's not uncommon to find equipment that's 35 years old or more. And older equipment likely requires retrofitting of sensors and connectivity and different compute endpoints in order to generate any kind of meaningful data from an IoT at all. So, however, and achieving those sorts of upgrades also means bringing in, kind of outside specialists with deep knowledge not only of that industry or that company, but also of the different equipment and what goes on at those different worksite locations. So it's very complicated, but it's a lot of effort that needs to get put into this. So how should we think about IoT? I don't really think that a network diagram, although technically accurate, really tells the story. Rather, let's look at the human body as an analogy. We have brains that do all of our heavy thinking, the computational load, if you will. But we don't use it for everything. There's autonomic behavior. Like, we don't need to think about breathing or drawing our hand away from a hot pan on the stove, well, at least not after the first time anymore. Our nervous system and our senses learn that behavior and can react to a different stimulus without the brain having to think about it really at all. They just do it. IoT works in much the same way. We have our cogitative functions, which we want to happen in the cloud, and we have our kind of reflexive or autonomic responses that we want to happen in what we call the fog. So this is a new concept, the fog, for some people. It's basically a local edge network that can react to expected stimulus, sensor data, with actions, with actuators. So things, if we're going to have millions or billions of them deployed, need to be cheap and therefore very limited from a battery, bandwidth, and computational capacity. So as much as possible, we want to keep the problems that they respond to at a local environment and keep them simple. So think about agriculture. If we have soil sensors that say that the ground is dry, we can simply have that sensor, connect to the fog and tell the actuators, turn on the sprinklers. and then our crops will thrive. So this is not a higher level cognitive problem. It's an autonomic response of sorts. On the other hand, if we have to make sense of all the data that all these sensors are producing and determine the new algorithm for optimal operations of a manufacturing plant, well, that type of higher level computation, we want to push up to the cloud, where we have virtually unlimited compute resources and power and bandwidth and so on. So just as we push complex problems to our brain to solve, we want to do the same thing in IoT. So we just need to think about how we architect our solutions along these lines. A couple of minutes that I want to spend is to just note about security. So mobile security has always been very challenging, but if you thought that was tough, wait till you get a hold of IoT. There's really tremendous amount of, So when it comes to IT's concerns regarding IoT, it's pretty simple. IoT introduces literally hundreds of thousands or millions of new entry points of attack vectors into the organization, and those devices often are not designed with any security in mind. So the question is next, can we use what we've learned about security on the internet and apply it to IoT? Well, the answer is not really. On the internet with traditional networks, we have general computing devices. We have encryption available to us. And if an issue is identified, we simply create and deploy a security patch. In IoT, almost none of these things are true. As noted a minute ago, to be able to deploy billions of devices, they must be cheap, which means they must be very limited. There's not enough computational power to support encryption, and very often no way to update the firmware if a patch is found. You just replace the device. So we need to look at approaches like limiting machine-to-machine communication, homomorphic encryption to address security. We need to think about system architectures. If we plan to connect 50 billion things to the internet, we better be very